morning. So this work was done thanks to a collaboration between the Department of Signal Theory and Structural Mechanics of the University of Granada. Unfortunately, none of my Spanish colleagues could attend the Congress, so finally I'm Nicolas Bochu and I will present that work instead of my colleague. Okay, well, so some words about the context and motivation. As most of you might know, composite materials are high-performance materials that are increasingly used in the industry, especially the aerospace and naval industry. But however, they might be vulnerable to impact damage and fatigue damage. And here you have an example of an impact damage. And usually when the impacted side is here, the damage starts on the opposite side of the material, creating matrix cracking, and then delamination, and then it spread out and propagate through the material. So they are especially vulnerable through the thickness direction. So already most of work have been done combining ultrasonic NDE and digital signal processing. But common approach are still offer still quite noisy solution. So the objective of this work is to obtain an accurate discrimination of damage in a CFRP plate using ultrasonic signals acquired under a classical C-scan mode. And to this end, we propose to generate damage map using a sparse all-pump model combined with signal Cepstral and unsupervised clustering technique. And the idea is to seek for solution that might be consistent with such a velocity map that we can see here that represent the impact damage, but that offer quite noisy solution, by adding some prior hypotheses on the aspect of the impact damage, such as that the impact damage will create a circular shape and also spread out in heterogeneous concentric circles with different damage level. So the proposed methodology to this end consists of 3 steps. A first step is the acquisition of the ultrasonic signals and the modeling through a sparse all-pole model. A second step consists of transforming those model parameters into Cepstral domain. And the last step is to use those Cepstral coefficients by classifying them using unsupervised clustering technique into several damage levels, which are sorted according to a reference signal. And basically, this reference signal is simply a signal taken from an undamaged area of the specimen. So about the experimental setup, we use a classical true transmission technique where we perform a C-scan of the specimen in immersion, and we use a frequency of 5 megahertz to excite the specimen, and then we just repeat the measurements over an area of 40 by 20 square millimeter around the impacted area. Once we get those over 800 ultrasonic signal, we propose to model them. And since we are propagating waves into a multi-layered system that consists of a finite number of layers, it is quite reasonable to assume that the ultrasonic response is sparse. So we represent the system by a discrete time transfer function that can be written as an all-pole filter with sparse coefficient that can be written up like this, where the maximal number of poles will be twice the thickness of the specimen. And with this notation, we just want to say that the cardinality of the AK is much smaller than twice this thickness. So we will see that most of the coefficient will be 0. And then to find those coefficients, we have to solve an analysis by synthesis scheme. So we can propose an objective function that consists of 2 terms, squared error term, which is this one, plus a sparsity term, which is this one, where we have this gamma that represents a regularization term to balance the squared error and the sparsity term. And this equation can easily be solved by convex optimization, and be aware that instead of using this objective function in the classical form with the A0 norm, we propose a relaxed version of it with the L1 norm. And once we get those coefficients, we will transform them in the Cepstral. We will apply a Cepstral transformation to get Cepstral coefficient. And then the last step of the methodology is once we get this Cepstral coefficient, we will apply clustering to exploit, clustering techniques are exploited to group the acquired signal into several damage levels depending on their similarities. And we will compare 5 different clustering techniques. Okay. A first simple result is just exploited in that we want to try to relate the number of non-zero coefficients in the sparse all-pole model with the damage levels. And if we perform that, we just obtain the following noisy damage map. But the point that is interesting is that we see that the impacted zone, which is in the middle, is related with a higher coefficient order of the sparse all-pole model. So it seems that the higher the damage level, the higher the number of coefficients that we need to use to model the ultrasonic system. And this might be consistent with previous results we observed that could explain this higher number of coefficients that are due to a rupture of the symmetry of the material that is examined. And then if we pass to the clustering results, if we observe first the results obtained using the Kamins and the Kamedori's clustering technique, we see that we can observe a quite clear impacting damage in the middle of the plate, but even though the maps are quite noisy and we need a quite huge number of clustering levels to obtain those maps. Instead, if we apply the linkage clustering technique, where the number of damage level is still set manually, we see that the damage is concentrated in the impact point and spread around concentrically, and that we do not have any noisy points in the undamaged area. So this maps looks quite consistent with what could be expected from the mechanical point of view of an impact damage. And then if we apply the DB-scan method, whose advantage is that the number of damage level is then automatically set within the method. Again, we obtain a result that is quite similar to that obtained with the linkage technique, and that looks quite consistent with a higher damage in the middle that then spread out concentrically. As a limitation, it should be noted that the calibration of this technique depends on the points belonging to the same neighborhood, so the clustering method is a little bit more expensive from computational point of view. And then the last technique is the ladder follower clustering method, which looks similar to the 2 previous ones, but even though the behavior of the damage propagation is quite noisy here, and we see that we need a huge number of damage level to reproduce it, so it is not really suitable for our purpose. So as a conclusion, we can see that the signals obtained from a highly damaged area require a larger amount of non-zero coefficient in the sparse all-pole model. Then unsupervised clustering technique combined with Cepstral analysis allow to discriminate between the different damage level, and it seems that linkage and DB-scan method offer the most current results with respect to what could be expected mechanically from an impact damage in a CFRP plate. Of course, as a strong limitation, it should be noted that at this stage, this study only offers a qualitative solution to the overall damage pattern distribution, and we are not able yet to determine the true thickness distribution of the damage. Even though one could expect to couple this method with a recent contribution we did, where we were somehow able to relate the sparsity to some mechanical properties, so maybe in the future we will be able to build some damage maps for each of the layers of the specimen. Other perspective would be to apply this methodology to plates with more complex damage mechanisms, such as multiple impacts or fatigue damage. And also the end of the final purpose of this study would be to connect the qualitative clustering levels to some macroscopic mechanical properties, such as the Young modulus reduction or damping ratio or whatever. So, thank you.